Hi everyone, this talk is about Portable UDFs, a feature that we built at Facebook. Before we get into the technical side of things, I want to spend a few seconds about introductions. So Rong is a Presto committer and she's a tech lead in the Presto team at Facebook. I'm Tejas, I'm a Spark committer and I'm a tech lead in the Spark team at Facebook. This is the high-level agenda of the talk. So let's dive into the first section about the motivation. So why do we need portable UDFs? To set the context, at Facebook, we provide multiple engines for people to solve their data problems. We have Presto, we have Spark, we have Digraph, which is a graph processing engine, and we have some stream processing engines as well. And we'll let our users pick any one of these systems based off what problem they want to solve. And so let's say if a user wants to create a report for employees, and in this report, they want to print the first name of the employee in uppercase. So if some user wants to write this query, they will use a function called as upper, which is already provided in all these systems. And so, yeah, they will refer to this upper function in the query, and then they will get their outputs. Now, imagine a case where the same user wants to create a report on the employees, and they want to associate certain score to every employee. And the way they associate a score to employees is based off some custom logic, which is specific to the business. And so in case of upper function, it was natively provided in these systems because it's a very basic function. But if you are to associate scores based off your some certain business logic, a database would not have those functions inbuilt for you. So what happens in this case? So in this case, user will try to author this function by themselves. So here on the slide, I have an example where a user starts off writing a query in Presto, and they search for that function in Presto. And turns out that it's not an inbuilt function in the engine. And they end up creating a new UDF for Presto, which implements their business logic. And so what does it mean when a user has to implement their UDF in Presto? So on this slide, I have an example of the array contains UDF in Presto. So this is just to give you guys a flavor of what does it mean to implement this. So first off, the user would have to learn about Java because Presto functions are written in Java. And they also need to learn about the interface of authoring functions in Presto. And they'll also learn about some internals about Presto. For example, what are data types in Presto and how to represent rows in Presto. So after learning all these things, they end up creating a Presto UDF for their business use case. Now, let's say after doing all this, the user wants to run the same UDF in Spark. And turns out when they try it, it fails. Why does it fail? The reason is because Presto UDFs are not same as the Spark UDFs. So here is the same array contains functions. This time on the left-hand side, you can see array contains for Presto. On the right-hand side, you can see it's the same UDF for Spark. And you can see that both of these are different. Like the first thing that I can notice is that Presto function is in Java and the Spark version is in Scala. So completely different language. And the way we express data types in both these engines is different. And even the rows, how we express the rows is also different. So users will have to learn about this. And in case of power users who care about performance, they might go one step ahead and try to learn about whole stage codegen in Spark. So that's one of the ways where people can get the maximum performance from a Spark function. And so after doing all these things, a user ends up creating two versions of this UDF, one for Presto and other one for Spark. So what are the pain points for users? Number one, a user will have to learn about engine specifics. As we looked earlier, they will have to learn about the interfaces of defining UDFs in both these engines. And if they want to refer the same UDF in, say, a graph processing engine, they'll have to learn about its internals as well. The other pain point is that over here, people will have to rewrite their logic 2 times. So going back to the previous slide, as we said, if you look at both these functions, one is for Presto, one is for Spark, they both are different. And you cannot just copy paste the code from one into other one. So it's basically a manual rewrite that one has to do. The third problem that we see is inconsistencies. So since the rewrites are done manually, it might happen that a user might have different semantics targeted for Presto and for Spark. It might just happen unintentionally. And we see often this in case of corner scenarios where, say, semantics for null is different. The same UDF might throw an error in Presto, but it might return null in Spark. And it's not really good for users because users expect if they call the same function, no matter which engine they call it from, they want to see the exact same outputs for this function. One more problem that we notice is versioning. So let's say a user starts off and they create version 1 of UDF in both Presto and in Spark. And then as time evolves, they want to change their business logic. And that means that they want to create a new version of this UDF. So whenever they do that, they have to be very sure that they make this change across both Presto and Spark versions. So if they create a V2 for Presto, and if they don't create a V2 for Spark, that means that both the engines will return you different outputs for the same UDF, which is bad. So a user has to make sure that both the copies of this function are always in sync. And the last problem that we notice is around releasing. So the way we ship these UDFs to our clusters is that we package all the different functions from different users into a single binary and ship it to our clusters. And in case of, let's say, if a user wants to get their function out quickly, it might happen that a Presto release might go faster or a Spark release might go faster. So your UDF might be in production at different points in time. And so you'll have to wait for the release to go out. And at times there might be, say, test case failures, which might delay your releases. And that means that you'll have to wait longer for your function to get in production. So these are the problems that we found when users were authoring functions. And in next section, I'll have Rongrong talk about how we try to solve them.
Thanks, Tedros, for the introduction. And now let's kind of get into, we have a problem, so how do we solve it? Or how do we develop UDF, portable UDF to solve the problem? So let's take a look at what UDF look like. So basically what we want to do is allow user to write a single version of the function in some way that it's independent from the engine. And then in all the compute engines we provide as service in Facebook, we would implement, or we will make these engines be able to run these functions. So this is an example of a Hello World example of how the portable UDF look like. Our first version of the portable UDF is supporting Java UDF. This is basically, as you can say, pretty vanilla Java implementation. We have a class, which in the class name would actually map to the function name. And then we'll have a convention of the package would be catalog.schema. So basically here, what you can see, the package has fb.example. So at the end of the day, this function will be fb.example.hello-world. And to specify an implementation of a function, we're using annotation. For example, on line 16 and line 21, you can see the add scalar function annotation. This marks that this function would be like an overload of this. So there are two versions of this function implementing this class. One is a traditional hello world that doesn't take any input and returns hello world. The other one, obviously, we developed that for testing purposes, takes a bunch of different types. And this is also a demonstration that these are all the types that we support. Basically, how we're treating the types is we allow users to develop functions using native Java types, and we have a mapping between the Java type and the SQL types. So here you can say we have Booleans and we have the numerical types, and then we have string or varchar, and then we have the collection type of array and maps here. In addition to these, we also added some annotation for data management. For example, there's ownership and description. So it will be easier to find who is maintaining the function and give users a better understanding of what does the function do. And there's also routine characteristics, which is used by the engine to decide on call conventions, determinism, etc. So in summary, we have three different types of function metadata that we're collecting. One set is the function management metadata, which includes things that engines don't really need, but then as a warehouse, we need them for management, better management and understanding, which are ownership, description, etc. And then there is the function resolution metadata, which is primarily used by the planner or analyzer side of the query engines. These would include the function signatures, call conventions, etc. And then there's the execution side of the metadata. These will be, what is the package info, like where do we find the function, like where do I find this, and what are the versions, whether the implementation is boxed or unboxed, etc. These are things that we try to directly extract from the Java implementation, so user don't need to specify it. So here's an example of like all the data that we automatically extract once the user write the portable Java function. Once they write the function and the code is reviewed and they are happy with the results and they commit this to the source code or the version control systems. Once it's committed, we'll run a background job to upload, extract all these informations, build the package, and then upload this to a function Metastore. And the function Metastore is what all the query engines would contact to when we're trying to execute the function. So now let's see that whether like this works for all the problems we're trying to solve. You've seen the slides before when Tedros mentioned this, right? So the number one reason we want to develop Portable UDF is we don't want to require users to learn all the engine specifics. This is solved because we're providing an engine agnostic API, and the API is pretty basic. That doesn't require users to understand the type systems or anything in the engine. They basically still use the native Java types. And the next set of the problems, rewriting logics or inconsistency in rewrite or maintaining multiple versions, these are all originated from having multiple versions of the code. Because we allow user to write a single version of the code in a single API, these problems are all solved as well, because now user only need to worry about this a single implementation. And then another problem is the release cycle problem. So how we solve this problem is basically when user commit on these functions, we will build packages, and these are the code base is maintained independent from the engine code base. And the release cycle is also maintained independent of the query engines. And the query engine would fetch these at runtime and load these libraries into their runtime at runtime. So this is, in this way, we also solve the problem that we no longer have to worry about different release cycles from different engines because the functions are independently released. And also, they are, for the most time, made available in the query engines only a few minutes after they commit their code. Now, it seems like we have a design that can solve the problems that we mentioned. Let's move on to talk about how these are actually implemented. I'll hand it back to Tedros to talk about how it's implemented in Spark.
Thanks, Rongrong. So let's look at how portable UDFs are executed in Spark. So I have an example query over here. It's select fb.example.hello world. And to this portable UDF, I'm passing input text as an argument. So when a user writes this query and submits it to Spark, let's see what happens. So when the Spark driver gets this query, it will parse this query and understand that this query is referring to a portable UDF. And whenever it sees that, the next thing that the Spark driver would want to do is fetch the metadata about this function. To do that, it talks to Metastore, and it gets some metadata about this function. So this is some example of what metadata we'll get. And I know that Rongrong had already covered this in her slides. So the first set of metadata that Spark gets is around some basic information about the function. So here we have the function name, the description, and who's the owner. And the other set of metadata that we care about is the function resolution metadata. So this is needed for Spark for doing the query planning. So over here we have the argument types, is the function nullable or not, that sort of information. And the last piece of information that Spark needs is function execution information. So for example, if it's a Java function, we want to know where is the jar for which has the code for this UDF, what is the class name, which method should Spark execute. So after Spark driver gets this metadata, the next thing that it will do is fetch the logic for this UDF. And so it talks to the V1 server and fetches the code for this portable function. And after it gets it, it will do some basic checks on it. Like a simple check would be that, hey, does the jar even has the class that we want or not? And so after it does all these checks, it will ship this jar to all the Spark executors and begin the query execution. So the way Spark is currently executing portable UDFs is similar to how it executes high UDFs. That is, the Spark executor would add the portable UDF jar to its class path. And at runtime, whenever Spark tries to execute, say, the function, it will just load this class in this class path and run the required method. Since we have three different ways to implement functions in Spark, after this, we try to do some performance benchmarking to see which one is better. So in this graph, I have plotted the performance profiling results for across these three approaches. So in the orange, you can see Spark native version. And so as we expected, if you implement your function in Spark natively, it will run super fast because over here, we can do whole stage code gen, and that is extremely fast. Now, the second approach to build functions is through high UDFs. As we all know, Spark supports us to invoke high UDFs. And so that is, as we expected, is slower than the Spark native way. And the third data point is around portable UDFs. So that is the blue bars in this graph. So over here, we see that portable UDFs are a little bit faster than high UDFs in certain cases. And the reason is that the data conversion cost. So whenever Spark has to run a high UDF, Spark has to convert the Spark internal row into something that high UDFs will understand. So that is the writable objects. And the cost of doing that is higher compared to when Spark runs portable UDFs. So there, Spark has to convert the internal row into primitive Java objects, which is faster. So let's move to the next section and understand how Presto executes portable UDF functions. So I'll hand it over to Rongrong.
Thanks, Tedros, for introducing how we implement this in Spark. Now let's move on to see how we do it in Presto. So first, we supported this in Presto as an external function. External functions is like SQL concept. Basically, we can say create function and external with the reference to where to find this external function. For this example, we're still using hello world. We have external name. That's basically the URL we'll need to use to look up this function in our function Metastore. And how we execute that in Presto, we are actually running them as remote functions in a separate cluster. This, for people who are familiar or not so familiar with Presto, because Presto servers don't provide query isolation, so running arbitrary customer code in Presto clusters can potentially cause reliability issues because we cannot fully trust the quality of this code. So we decided to run them outside of the JVM for the worker to provide some isolation just in case these functions fail, so it doesn't fail other queries. Let's look at how do we make that happen. So basically what we do is when we receive a query at Presto coordinator, we need to do some planner change. Basically what planner is trying to do is taking a project where these expressions would be, or these functions would be, we'll analyze the expression to figure out which part can be run locally and which are the functions that we need to invoke remotely. We'll do a planner change according to this. The reason we want to do this is so we can still provide a batch operation. So when we're sending the query plan to the Presto workers, and then the Presto worker, in case of running remote functions, need to talk to UDF server, what we're doing is we're sending a batch of rows to UDF server together, rather than invoking the UDF server on every row. Since these are remote calls, invoking the function on every row could be quite expensive. So that's what we're trying to avoid. So let's take a look of this example. It's a bit tiny, so it's not easy to read, but highlighting what is going on, here we actually have 3 remote functions. There's one remote function, number 1 is a separate projection of a remote function. Number 2 and the number 3. Number 3 is actually depending on number 2. So we need to compute 2 before we can compute 3. So the planner, what the planner does is basically, instead of single project, we're actually breaking this into 4 projections with 2 local stage and 2 remote stages highlighted here. And for these remote stages, you can say that we can run the remote function 1, remote function 2 together in one stage. But then we need to run a local, and then another remote function number 3 actually needs to depend on the results of all these things. So these are broke into different project operators. So on each operator, we can still process a set of rows in like a batching API. So at runtime, this is what it looks like on Presto worker. Presto worker would see that this plan would need to run local project, which business as usual. And when it sees remote project, it will try to send a request to UDF server. And then UDF server would so this API is basically logically just the invoke function with the function handle and the input data. And UDF server, when we see this function handle, which is more or less, you can understand it as the URL we're mentioning previously, we'll give this URL and use it to retrieve the whole function metadata from the Metastore. And then based on that information, UDF server can figure out, okay, these are the packages I need to load, and these are the method I need to invoke. And all of those can be code-genned. And we'll process this on all the inputs and then send all the results back. And yeah, so that's how it works in Presto. That's all for the details of how we implement it in Presto. And now let's open up for questions.